So in the last class we have been talking about examples on non-commutative rings. We are going to complete this chapter today with an example on non-commutative field. So let us start with the definition of the field, then we will build a field that is not commutative. A field is a commutative division ring with unity. Now, if you are not sure the field is commutative, if you just say a division ring with unity, that is called a skew field. A division ring with the unity is a skew field. But if you are sure it is not commutative, a non-commutative division ring is called a strictly skew field. So these are the definitions which we need to know on this skew field. So what we are going to do is we are going to give you an example of a strictly skew field, meaning the multiplication is not commutative on this field. And this field, the field which you are going to give is called quaternions by Hamilton. Quaternions by Hamilton. So when you want to build a field or a ring, what we need is we need elements and two binary operations, addition and multiplication. And with the addition it should be a commutative or abelian group, and in this case the multiplication is non-commutative. And by the term division ring means every element of this ring has a multiplicative inverse. So let us start with the elements of the field. The elements of the quaternions are the direct product of real numbers. R is the set of real numbers. Now we need to define the addition. Addition is defined as let A1, A2, A3, A4, comma B1, B2, B3, B4 belongs to, we'll call this one as H. H for Hamilton. Okay, that is H is equal to R times R times R times R. If you take these two elements, the sum of these two elements, that is A1, A2, A3, A4 plus B1 comma B2 comma B3 comma B4 is equal to A1 plus A1 plus B1 comma A2 plus B2 comma A3 plus B3 comma A4 plus B4. So clearly H with plus is an abelian group with the identity 0, 0, 0, 0. Okay. Now the elements of this H can be written in a different way. Instead of writing like this, what we are going to do is the elements of R are generated by 1 equals 1 0 0 0, I is equal to 0 1 0 0, J is equal to 0 0 0 0 1 0, and K is equal to 0 0 0 1. So that A1 comma A2 comma A3 comma A4 is equal to A1 times 1 plus A2 times I plus A3 times J plus A4 times K, where this multiplication is the multiplication on R. Okay, that is how we are going to define the elements on H. So with these generators we are going to define the multiplication. When we define the multiplication, what we have to do is the multiplication should be non-commutative and it has to be associative and it should have inverse for every element. With these three ideas in mind, the multiplication is defined like this. Multiplication is defined like this. That is I square is equal to J square is equal to K square is equal to minus 1. Ij is equal to K. Jk is equal to I. Ki is equal to J. Ji is equal to minus K. Kj is equal to minus I. Ik is equal to minus J. Why you want to define like this? When you multiply two elements like A1 1 plus A2 I plus A3 J plus A4 K times B1 1 plus B2 I plus B3 J plus B4 K. When you multiply this, you will get terms of these form along with the coefficients. For example, if you multiply B2I times A3J times B2I is A 3 j b2 I. So you have ji here. So when you have this definition, our multiplication is complete. Okay, with this you can get a1 comma a2 comma a3 comma a4 times b1 comma b2 comma b3 comma b4 equals you have 4 terms here, and each term will have 4 components. So this will be a1 b1 minus a2 b2 minus a3 b3 minus a4 b4 comma. Now next one is a1 b2 a2 b1 then a3 b4 minus a4 b3. This is the second term, and the third term will be a1 b3 minus a2 b4 plus a3 b1 plus a4 b2, and the last term will be a1 b4 a2 b3 minus a3 b2 plus a4 b1. Because if you expand this one, for example, just we'll take one example. When you take a2 times b3, this is actually a2i times b3j, so ijk, okay, and that is where a2 b3 is coming here, but a3 b2 is actually minus k, that is ji, and that is why we have a negative here. So this is the definition of the multiplication. With this definition, the multiplication or the group H with the multiplication is a non-commutative group. Because it has got the inverse, I'll show you what the inverse of every element with the identity as 1, 0, 0, 0, 0, or that is equal to 1. Okay, and the multiplication is distributive over addition. So with this notation, like a1 comma a2 comma a3 comma a4 is equal to a1 times 1 plus A2 times I plus A3 times J plus A4 times K. The multiplication can be written as A1 comma A2 comma A3 comma A4 times B1 comma B2 comma B3 comma B4 as A11 plus A2I plus A3J plus A4K times B11 plus B2I plus B3J plus B4K. Okay, and that is actually not equal to B11 plus B2I plus B3J plus B4K times A11 plus A2I plus A3J plus A4K, because Ij is different from Ji, Ik is different from Ki, and Jk is different from K. So multiplication is not commutative, and we know that we have a identity. Now we need to show that it's a division ring, meaning it has got a multiplicative inverse for every non-zero element. So let A1, A2, A3, A4 be a non-zero element. Define A square is equal to A1 square plus A2 square plus A3 square plus A4 square. This is possible because these are all real numbers where AI belongs to R. Then A1 comma A2 comma A3 comma A4 inverse is going to be A1 by the norm square. This is a norm square, we'll call it as norm square, comma A2 minus A2 by norm square, comma minus A3 by norm square, comma minus A4 by norm square. Because A1 plus A2I plus A3J plus A4K times we'll take this one out, so we'll have A1 1 minus A2I minus A3J minus A4K times 1 by A square, that will be equal to 1. I'm not going to compute this one. You can multiply and we'll see that the whole thing will be A square. Okay, so that implies the inverse of A1, A2, A3, A4 is this. So for every non-zero element in H has a multiplicative inverse. The only thing which remains to prove is that the multiplication is distributive over addition. So verify, I'm not going to do that, that is just an exercise. Verify the multiplication is distributive over addition. This is true actually because hint, the elements of H are from R. And if you take the normal addition and multiplication, this is distributive. So from here we can easily prove that the new definition of multiplication is distributive over addition, and that implies H is a non-commutative division ring with unity, and that means H is a strictly skew Let us do some problems using this strictly skew field, the quaternions. So the first problem is we are going to try is compute. Let us say 1 plus 3i 2j minus k inverse. So first we expand this one, and that is going to be 2j minus k plus 6ij minus 3ik inverse, and that is equal to 2j minus k. This is k, so plus 6k. This is minus j, so this is 3j inverse, and that is equal to 3j plus 2j, 5j. This is going to be minus 5k, sorry, plus 5k. Inverse. So here A0 equal to A1 equal to 0, A2 equal to 0, A3 equal to 5, A4 equal to 5. So mod A square or norm A square is equal to A1 square plus A2 square plus A3 square plus A4 square, and that is equal to 5 square plus 5 square is equal to 250. Sorry, 50, just 50. This is going to be just 50. So the inverse of 5j plus 5k will be minus 5 by 50 j minus 5 by 50 k, and that is equal to minus 1 by 10 j plus or minus 1 by 10 k. The next problem we are going to try is this. Find the center of H. Meaning center of H with a multiplication, or probably H star with a multiplication. Okay, this is actually the multiplicative group of the ring, with the non-zero elements. So the center is defined as elements from the group such that HK is equal to KH for all K in H star. So this H and K are four tuples in which only the first component is guaranteed to commute. I, J and K cannot commute. So this the center of this will be A, 0, 0, 0, where A is different from 0 and A belongs to R. Okay? Because if you have I or J or K, if any component exists here, it won't commute with every element of H. So the only elements that can commute to the rest of the elements are A, 0, 0, 0. So this is a center. We'll do one more problems before we complete this chapter. We know that if F is a field and f of x is the ring of polynomials and f of x belongs to f of x, and the degree of f of x is equal to n, then f of x has at most n distinct zeros and distinct zeros. That is when f is a field. But if f is a strictly skew field, this is not the case. So let us see, let H be the quaternions and x square plus 1 belongs to h of x. So this is a polynomial in this ring of polynomials. what we are going to show is that this polynomial can have more than 2 zeros. I square is minus 1, j square is equal to minus 1, and k square is also equal to minus 1. That is how we defined. So this implies I, j and k are zeros of x square plus 1 that belongs to h of x. So that implies f of x in a f of x belongs to, let us say, just h of x, where h is a skew field, strictly skew field, then f of x can have more than n distinct zeros where n is the degree of